So in classification task, we are given label data we have, right? So label data means images are there, or let's say input data points are there, and labels are also there, right? And we will learn a machine learning model using label data, right? So in supervised learning, I discussed two types of task: classification and regression, right? Yeah. Yes. So in supervised learning, classification and regression, right? So in regression, we will predict real valued output for given input, and in classification, we will predict class, right? Now input may belongs to one particular class, right? So suppose there are 10 classes, and input may belongs to class 1, class 2, or class 3. So that type of problem is known as classification problem, right? So today we will see classification problem, where we will do supervised learning, which means we are given label data, right? Okay, so we will see here one model. We will build one model using MNIST dataset. So MNIST is a image dataset, and using this dataset, we will do classification task, right? Then we will see several performance measure: cross validation, confusion matrix, precision recall, right? ROC curve, and then we will see types of classification. So multi-class classification, multi-label classification, multi-output classification, right? So these are the nothing but the various types of classification tasks, right? Okay, so let's start. Okay, so let me first share the slide and the Jupyter notebook, right?
Hey, just one quick question.
Yes, yes.
Based on the quiz list which was sent, we have the next quiz. I mean, tomorrow we have one for end-to-end, but after that
Mhm,
we have a quiz for linear regression. Uh,
mhm.
so will that also be covered in today's and tomorrow's lecture, or I mean that's going to change in terms of the quiz?
No, no. So today and tomorrow I will cover classification. So I think regression is already covered, right? So
I mean,
yes. So
we
house
did.
price prediction is there a regression task, right?
Oh, okay. So we are not going to go into any more detail in linear regression. That is,
Okay.
I mean,
So
whatever
let
is
me.
covered.
Yes, yes. So let me just confirm it with Gajend, and then
Sure.
Gajend will inform you, right?
Okay. Yeah. Thank you. Thank you so much.
Can we also publish the list of topics for quiz? That will help because there is some confusion regarding what all is the coverage for the quiz.
Okay, okay. So yes, so Gajendra will inform you. So I think topic end-to-end machine learning will be there in quiz.
Yeah, so in end to end, right, there are various
Mhm.
things, so we do not know which topics and what detail are we expected to cover.
Okay, okay. So I
And
will ask Gajendra, right? So
better
he will.
down for doing a project, right?
Mhm. And end-to-end, we mainly cover the regression
List
part,
of
right?
topics.
So house price prediction is a regression task, right? Because we were predicting their the real valued output given sub inputs, right?
Yeah,
So
that is
I
clear.
have yes, yes. Yes, so I have shared the Jupyter notebook and the PPT in the chat. Yes. Yes, so machine learning can be machine learning task can be categorized in classification regression when we are doing supervised learning, right? So here mainly you can categorize in three parts: supervised learning, unsupervised learning, and reinforcement learning, right? So I already discussed all these three parts, right? So in supervised learning we are given label data, right? So input is given and the corresponding output also given, right? And using input and output pair, we will learn a machine learning model. In unsupervised learning task, only inputs are given and we don't know the output labels, right? And reinforcement learning, we will have reward schemes, right? So in reinforcement learning, we will train one agent, and based on some reward, we will train our model, right? So for example, in gaming, right? So if you are designing a game, so in game you can use reinforcement learning where you can train a model, right? So model may take steps depending on whether the reward is positive or negative, right? So mainly here in today, I will cover the classification part, right? So here in supervised learning, human supervision is available, which means the label data is available, right? Because we label the data, right? So we are labeling the data, and that label data is available to us, right? Okay, so that's label data comes under supervised learning part, right? Incrementally, we can learn model when we have when data is not available, right? So for example, at time t is equal to 0, we don't have the complete data, and let's say at time t plus 1, we are having some more data, right? So data we are getting incrementally, then we can learn model incrementally. So that types of learning is also possible, and that types of learning is called incremental learning, right? So where we are learning model incrementally. Yes. Any doubt? Okay. So let's start the classification
I have a
class.
question.
Yes.
Are we going to cover multi-output as well?
Yes. So multi-output is yes. So I will cover briefly, right? So in multiple output means we are having multiple outputs, right?
Yeah.
So input. So you can think in multi-output. Suppose if you are predicting, let's say, two types of tasks. So, for example, let's say given a image uh, and given a image of person, you are predicting, let's say, person height and person weight, right? So it's a multi-output classification, right? So multi-output regression, because you are predicting two real values. Likewise, in classification, if you are predicting multiple things, that comes under multi-output classification, right? Okay. So here in the classification is the task of identifying to which category a new observation belongs, which means, uh, let's say, given a image, we want to predict its category, right? And here, since label data is available, which means we already know the input-output pair, right? So for example, let's say some bunch of cat images are given, so we already know this is the cat image and this is the dog image, right? So like that, we are given some label data where we already have input output mapping, right? So for each input we are having corresponding output, right? So in other words, that output is called the label. So for example, here the label of this image is cat, right? And suppose if you are doing a binary classification task, in binary classification task, there are two classes, right? In multi-class classification task, there are more than two classes, right? So since here, let's say if your task is to predict whether the given image is a cat image or not a cat image, right? So since here you are doing a binary task, you are predicting a binary task. So this type of classification is called binary classification, where we are exactly having two classes, right? So here, what are the two classes? Cat versus not cat, right? So these are the two categories. Another example is cat versus dog classifier, right? Suppose you are having some cat images, some dog images, and your our goal is to predict whether a given image is a cat image or dog image. So again, in this example, we are only having two classes. So therefore, this type of classification is also called binary classification. Binary means when we are doing classification tasks using two classes, right? Okay.
So,
So yes.
so sorry, one question. For the other example which you said, C2 where cat and dog we are getting, right?
Mhm.
But the model will give three output, right? It will give whether the image is cat, whether the image is dog, or whether the image is neither, right? So the output of
No, no,
that
then
model
that
will be
yes. So then that model is called the then we are doing multi-class classification, right? So because we are having more than two classes, right?
okay. So if it is binary classification, and if the input is say an image of an elephant, it will still classify it between cat and dog only.
No, no. When model is predicting one out of two class, one out of two, and there are exactly two classes. The two classes can be either positive or negative, or 0 or 1, cat versus not cat, cat versus dog, right? So, but there has to be exactly two classes,
Okay.
right? If we
Okay.
are solving more than two classes, then it's called multi-class classification problem, right?
Okay. Got it.
Okay. So here, since we are exactly having two classes, so therefore we are solving a binary classification task, right? Binary means we are predicting one out of two classes, right? Okay. The another example is spam versus non-spam email, right? So let's say if you want to predict, if you are building a spam classifier, and your task is to predict whether a given email is a spam or not a spam. So again, this task is a binary classification task, right? Because here you are categorizing email into one category. Either this email can be spam or not spam, right? Okay. So this is again a binary classification task. Now let's take another example. Suppose if you want to classify news article depending upon its category. So for example, news article may belongs to the technology or sports or entertainment. So since here we are having more than two classes, so this type of classification is called multi-class classification, right? Okay. So what is the classification? So classification means we are categorizing image to its class, right? So for the training data, we already have input output pair. We already have inputs or images with labels, right? So input. So suppose if you are building a model using images, then in that case, inputs are nothing but the images, right? And so for example here this this image you can think like a input, and label is apple, right? Here this is an input image and label is banana, right? Okay, so training time we will use images and labels to train a machine learning model, and test time we will predict for a given image we will predict its class, right? So test time we are given only images, and our goal is to predict image class, right? So we are given images without label at the test time, and we will predict its class, right? Okay. So how does classification training works? So yes. So suppose if you want to build a machine learning model to classify, let's say, these fruits, then here as you can see how many classes we are having: one, two, three, four, five. So we are solving a five class classification task, right? So since classes are okay, I think one, two, three, and four. Yes, so we are solving a four-class classification task. So since we are having more than two classes, so it's a multi-class classification task, right? Okay. So what we will do, we will use training data to train a machine learning model, right? So in training phase, we will use label data, right? So we will use images, we will use input. So here input means images. So we will use input images, and we also have the labels, right? So we already know this is the apple image, banana image, right? So that type of label we already have during the training phase. So we will use this label data to train a machine learning model, right? And then at the test time, for a given image, we will using this model, we will make we will predict its class, right? So for example, given this image, we will predict its class, right? So test time we will
Sir,
use.
I have a doubt.
Yes, yes, yes.
Sir, like in previous slide, we are classifying between like all the fruits. So, is it possible to classify between different type of images, like one apple, one cat, one different images?
Yes, yes, you can do that, right?
So that is also like multi-class classification.
Yes, yes. So if you are if we are having more than two classes, then it's a multi-class classroom, right?
Okay, sir.
But yes, binary classification means we are having two classes and we are predicting one out of two classes, right? In multi-class classification problem, we are having, assume we are having capital C many classes, where capital C can be 10, 20, any number it can be, right? So we are given capital C many classes, and we are predicting one out of capital C category, right? And we also have one more type of classification that is called multi-label classification. So in multi-label, what we do, within a same image, we can predict multiple classes, right? So that's a different type of classification that I will discuss later, right? So here you can assume we are predicting either for the binary case, we are predicting one out of two, or for the multi-class classification problem, we are predicting one out of C classes, right? But for multi-label, if you it is possible to predict multiple classes for the same input, right? So for example, within the same image, you are having apple and banana, right? So then model must predict both classes, apple and banana. But that type of classification is known as multi-label classification problem, right? But in multi-class, it is not possible. In multi-class, one image can have exactly one class, right? Okay, so assume here we are doing a multi-class classification problem. So we will train this machine learning model, and then we will use this same model at the test time, right? So for the given image, we will predict its label. Yes. Okay. So how can we train a machine learning model using images? So as I discussed before that. If we are dealing with images, then we need to first convert image to some numerical representation, right? Because machine learning model or machine can only understand numbers, right? Machine can only understand uh, numerical values, right? So what we will do, we will first convert images to some numerical representation, right? So there are several methods to convert image to some numerical representation, and I have already discussed several techniques. How can we convert image to numerical representation? And one simple method is flattening. What we can do, we can flatten image to get a one-dimensional vector. So, for example, if we have this image of size 28 by 28, right? Assume this apple image size is 28 by 28. What we can do, we can flatten this 28 by 28 image to get a vector, right? Okay. So suppose yeah. So suppose you have image of size, let's say, for the sake of simplicity, assume image size is 5 by 5, right? Width is 5 and height is 5. So in this image, how many pixels will be there? 25 pixels, right? 5 into 5, 25 pixels will be there in this 5 cross 5 image, right? Okay. So how can we convert this WH image into some numerical representation. Simple method is flattening. So what we will do, we will flatten this image to a vector of size 25 cross 1. So it depends on how you are converting. Either you can convert this image to some column vector or to some row vector. So if you are converting image to column vector, then size will be 25 cross 1. If you are converting in row vector, then size will be 1 by 25, right? And how, yes, any doubt?
Yes, sir, but how we will decide ki, like whether we have to go by row wise or column wise?
It doesn't matter, right? Because accordingly we will adjust our model. So it's just a matter of multiplications, right? So if we are doing, because we have to match the dimensions, right? So we can adjust dimensions. So for example, if you are doing if you are storing row wise, then you have to pre-multiply. If you are doing column wise, then we will post multiply that matrix, right? So it doesn't matter. Accordingly, we will adjust it, right? Okay. So
Okay, sir.
yes, yes. So how can we convert this image in? So let's say if you are flattening this image in a row vector, right? So row vector, how can you? So there will be 5 rows, right? Yes. So first row, second row, third row, fourth row, and fifth row, right? So what you will do? You will store first row, then you will store second row, then you will store third row, then fourth row, and then fifth row, right? So if you arrange row wise, then what will be the size of this row vector? 1 by 25, right? So, and if you are arranging column wise, you can also arrange column wise, right? So column wise, how can you arrange? So let's say if you are arranging column wise, then it will be nothing but the first row, then second row, third row, likewise, right? Fifth row. So now in this case, you will get a column vector of size 25 by 1, right? Okay, so in my example, I'm arranging 5 by 5 image, or let's say W by H image row wise, right? Okay, so if I'm taking a image of size 5 by 5, then there will be 25 pixels, right? 25 pixels will be there. 1, 2. Yes. So as you can see here, there are total 25 pixels. So these pixels are nothing but the feature. So how many features we are having if we have a image of size 5 by 5? 25 features will be there, right? So if you see this vector, in this vector, there will be 1 row and 25 columns, right? So each column is nothing but a feature of this image, right? So first column, let's say second column, third column, and so on. And last will be the 25th column, right? So this first column is nothing but the first feature of this image. Second column is nothing but the second feature of this image, right? So likewise, in this image, we are having total 25 features, right? Any doubt in this example? Okay.
So each pixel will be the vector of RGB. That,
Yes, so here I'm assuming a grayscale image, right? So in grayscale image, we are only having one channel for the sake of simplicity. But yes, if you are dealing with the RGB image, there will be 3 channels, right? R, G, and B. So then the image size will be the 5 into 5 into 3, because 3 are the number of channel R, B, and G, right? Then in that case, the size of the vector will be 1 into 25 into 3, right? So 1 into 75.
So do we have libraries which will give you the grayscaling of if you give a gray like image, then we can convert it to grayscale.
No need to convert the grayscale. We will directly use RGB image as it is. But yes, we have libraries using which we can convert a RGB image to grayscale image, right?
Okay.
But it's better to use RGB images, right? Because if we are converting RGB images to grayscale images, and then in that case we will lose color information. And let's say if the task that we are performing depends on the object color, then some accuracy will be lost, right? Because we are losing that property. So for example here, let's say you are predicting the fruits, and here each fruit has its color, right? So since you have converted images into grayscale, color information will be lost, right? So because here in classification, color also play a important role here, right? So we will not convert RGB images to grayscale images, and directly we will use RGB. So in RGB,
Dr.
what? Yes, yes.
Yeah, sorry, Dr. Praveen. So this 5x5 matrix, what does it store? A zero means zero.
No, so this 5 by 5 is a grayscale image. In grayscale image, we only have one channel, right? So
Right.
so there are 25 cells in 5 by 5, or you can think in 5 by 5 image there are 25 grids, and each grid contains a pixel value. Pixel value may range from 0 to 255, right? Because if we are storing each pixel in 8-bit, right? In 8-bit, we
Okay.
can represent 0 to 255 values, right? And if we are storing in 16-bit, then we can also store multiple shades of a color, right? But here I'm taking 8-bit example. So in 8-bit, we can take 0 to 255 range, right?
So every cell will be then converted into this 1/25 thing that you mentioned, right? So whatever the value is, it will be then transported in this kind of single row.
Yes, yes. So we are storing this rectangular image, or let's say square image, uh, in row wise fashion. So here, if you are arranging in a row vector, then what we will do, we will first store first row, then second row, then third row, and so on. So this is nothing but the first row of our image, second row our image, third row of our image, and we will arrange here row wise, right? So since in each row we are having here 5 values, and there are total 5 rows, so therefore total number of values will be here 25, right? So this vector size of this row vector will be 1 cross 25, right? The important point here is that each value here you can think like a feature of this image, right? So since there are total 25 cells in this image, so it means there are total 25 features in this image, right? Okay, so let's take another example. So suppose let's say you are having 3 images: image 1, image 2, image 3, right? So there are 3 images, and suppose the number of features in each image are 786, right? So there are total 786 features in each image, which means there are total 786 pixels. Just like here in this image, we are having 25 pixels, right? So there are 25 pixels. So that 25 pixels we can arrange in a row vector, right? So here also we are arranging each image row wise, right? So this first row vector is nothing but the first feature of um, first image feature, right? Second row is nothing but the uh, feature vector of second image, right? So this vector is called the feature vector of this image, right? Because here we are having 25 features, right? So we are having a vector of features, vector of 25 features. So that's why this vector is called feature vector, right? Okay. So this first row is nothing but the feature vector of first row. And since in this here we are having total 786 columns, or you can say total 786 features. So what we can say, in each image we are having 786 features, right? So, and this cell, what this first cell will tell you, this first cell is nothing but the image 1 first feature. Second cell is image 1 second feature. Similarly, this cell is nothing but the image 2 first feature. This cell is image 2 second feature, right? And there are total 786 features, right? So as you can see here, we are arranging inputs in a tabular form, right? We are arranging inputs in a tabular form where each input is a row vector, right?
Sorry, Dr. Praveen. So
Mhm.
one thing, how did we arrive 786? I thought there were 255 thing, right?
Yeah, so 786 is a random number, so you can so let's if image size is a 25 by 25, or let's say 32 by 32, then this number will be 32
1024.
square. Yes,
Okay.
1024. Yes.
Oh, okay. Okay.
Okay. So here we are first converting a rectangular image W by H image into a uh, row vector, right? So after converting a rectangular image, or after flattening a rectangular image to a row vector, we are arranging our data into a tabular form, right? Where then how many rows will be there? Total number of images, right? So if there are 10 images in our data set, then in this tabular form there will be 10 rows, and there will be 786 column, because here each input or each image contains total 786 features, right? Okay. Now, since we are doing a supervised learning task, we are solving a supervised learning problem. So therefore, for each image, we will have a corresponding label, right? So this matrix is called the feature matrix, because here we are arranging features of all images, right? So suppose if we are having 3 images in our data set, then the size of this feature matrix will be 3 into 786, right? Now, since we are having 3 images, so there will be 3 output corresponding to each image. So, for example, for image 1, output is apple. For image 2, output label is banana. For image 3, output label is again apple, right? So, we will have a one vector of output labels, right? So, there will be two uh, uh, matrix. One will be the feature matrix X, and another will be the output vector Y, right? So for example, let's say for this image, output label is, let's say, dog, right? So this 1 by 24 is nothing but the feature vector of this image, and the output label is dog, right? Okay, now we will use this feature matrix X and output label vector Y to train our machine learning, right? Okay. Yes. So since we have converted each image into some numerical representation, so therefore now our machine learning model can understand this numerical representation, right? Because directly we cannot pass these images, these raw input images to any machine learning model, right? So we need to first convert image into some numerical representation, then only our machine learning model can understand it, right? So this is the reason why we are flattening images into row vectors, right? Okay, so any doubt here? We will have two matrices One is the feature matrix X, another is a output label vector Y, right? If there are three images, then the dimension of this output vector will be 3 by 1. If there are n images in our data set, then the dimension of this output vector will be n cross 1, n number of rows and 1 column, right? Okay. So after converting images into matrix X and label Y, we can divide our data into two parts, training part and the testing part, right? Yes. So here, one point you can note here, I'm using superscript and subscript notation. So here, the superscript is means the image ID. So for example, as you can see in first row, I'm using one as a superscript, which shows that this feature belongs to first image. Likewise, here in the third image, the superscript will be 3, right? Because here we will write image 3 features, right? Similarly, subscript will tell you the number of feature, position of feature. So for example, here the subscript 1 means uh, this is the first feature, right? And this subscript 2 means this is the second feature. Here subscript 786 means this is the 786 feature, right? And the superscript will tell you the image number. So for example, one this particular cell means first image, second feature. So here first image 786 features, right? Likewise, we will have a superscript in output vector Y, right? So here superscript 1 means this is the label for first image, right? Similarly, Y2 means this is the label for second image, right? So superscript will always tell you the image ID, and subscript will tell you the uh, position of feature, right? First position, first feature, second feature, like that, right? Okay. Okay. So after converting data sets into this tabular form and the vector form X and Y, we will split our data into training part and testing part, right? So for example, let's say 80% of rows you can take as a training part, and 20% of data you can take as a test part, right? Or let's say if you are doing some hyperparameter tuning, then you can also divide this data set into three parts: training part, test part, and validation part, right? Okay. Now you will use this training part to train a machine learning model, and we will test the performance of this machine learning model using test set, right? Okay. So any doubt in this example? Yes. So this slide I have already discussed, right? So if we are having two categories, if we are having two classes, then task is called, the task is called the binary classification task. If we are having multiple classes or multiple categories or more than two categories, then that type of task is known as multi-class classification task, right? Okay. So here in this session, we will build a model to classify handwritten digit, right? So, and to solve this task, we will use MNIST dataset. So MNIST dataset is a handwritten digit dataset, right? So where we are having images of handwritten digit of 0 to 9, right? So for example, this is a handwritten 5-digit image, right? So now, since the handwritten digit image can be 0-digit image, 1-digit image, or let's say 9-digit image, so there are total 10 categories, right? There are total 10 classes, 0, 1, 2, and so on up to 9, right? So since we are solving so there are more than 2 classes. So therefore, this type of classification is the multi-class classification task, right? Because we are having here multiple classes. So given an image, our job is to predict its class. So for example, this model should predict this is a handwritten digit 5 image, right? So its class should must be 5, right? Okay. So to solve this problem, we will use MNIST dataset. So MNIST dataset contains 70,000 images, right? 70,000 handwritten images, and for each images we are having label, right? So this MNIST is a label dataset. Label means for each image we are also know its label, right? So for example, we know that this is a five handwritten 5-digit image. This is a handwritten 0-digit image, right? So for each images its label is given, right? Okay, and the size of each image is 28 by 28, right? And yes, so there are so width of image is 28 and height of image is 28, right? And all these images have been size normalized and centered in a fixed size image, right? So these are nothing but the pre-processed image, right? So where size of all images are 28 by 28 pixels, right? And the full
What
form,
do you mean by size
yes,
normalized?
size normalized means because images can have a different size, right? So for example, some images may be 30 by 30 or 30 by 32. So we have converted all
Okay.
images to the same size, 28 by 28 pixels, right? And the full form of MNIST is nothing but the Modified National Institute of Standard and Technology, right? So this is a standard data set for handwritten digits, right? And yes, as I said, this is a label data set, right? So using this data set, we can do supervised learning, right? And it's a very basic data set, so that's why this data set is also called hello world of machine learning, right? Because it's a very basic data set to do the multi-class classification task, right? Because here we are having more than 2 classes, so we are doing a multi-class classification problem. We are solving a multi-class classification task, right? Yes. So Jupyter, I have already uploaded. I have already shared in chat section. So please download the Jupyter notebook file. Yes. So let's go to. Okay. So now we will use scikit-learn dot data sets to import MNIST data set, right? So here we will use from scikit-learn to dataset import fetch underscore openML, right? And using this fetch underscore openML, we can load our data sets, right? So here MNIST underscore 784 is nothing but the name of dataset, right? And for this dataset there are several versions. So suppose if I'm interested in version 1, so here I'm writing version is equal to 1, right? So it will fetch a MNIST database, right? And it will store that dataset MNIST dataset to this MNIST variable. Now this MNIST variable contains this complete dataset, MNIST dataset, handwritten dataset, right? Now using that complete data set, I'm extracting inputs and outputs, right? So here writing MNIST in bracket data, which means I'm extracting inputs, right? X matrix is nothing but the input matrix, right? Feature matrix, and Y is here the output labels, right? So target means output label. So by writing MNIST in bracket data and MNIST in bracket target, I can extract input X matrix and output matrix from this data set, right? Where X and Y are nothing but the this matrix. Yes, this matrix, right? So X means input matrix where we are having all inputs, right? In columns, we are having features, and in rows, we are having inputs, right? So, for example, if we are having 50,000 inputs, then there will be 50,000 rows in this X matrix, right? And suppose if there are n, suppose if there are, let's say, 500 features in each input, then there will be 500 columns in this matrix, right? And y is nothing but a vector, right? Where the dimension of this vector is nothing but the number of data points in our data set cross 1, because there are one column and there are number of rows equal to the total number of points in our data set, right? So, for example, if you have three images, we will have 3 rows in this vector, or the size of this output vector will be 3 by 1, right? Yes. So after writing MNIST bracket data and MNIST bracket target, we can extract input and output, where X is nothing but the input matrix, right? So in this matrix, inputs we are arranging row wise, and Y is nothing but a output vector, right? Where we are having output for each inputs, right? Okay, so if you print here the size of X and Y, so since MNIST data set, there are total 70,000 images. So therefore, in each image, so there are total 70,000 images. So therefore, in this X matrix, input matrix, there will be total 70,000 rows, right? And since in each image, we are having total 784 features. So therefore, in this X matrix, there will be 784 columns, right? And this 784 is nothing but the size that you will get after flattening a 28 by 28 image. So if you multiply 28 into 28, you will get 728, right? Sorry, 784, right? So 784 you will get when you multiply 28 into 28, right? Because the size of this image is 28 by 28. If you flatten this image, you will get a vector of size 768, right? Sorry, 784, right? Okay, so the size of this input X will be 70,000 into 784, which means there are total 70,000 inputs, and in each input there are total 784 features, right? Now, since we are having 70,000 inputs, so therefore there will be 70,000 output labels, right? So if you print size of this output vector Y, you will get a vector of size 70,000, which is nothing but a column vector of size 70,000 cross 1, right? Yes. So we are given 70,000 labeled images in a tabular form, where we are having rows and columns. So yes, so this slide I have already explained. So here we are having 3 terms: instance, features, and labels. So instance means image. So each image is an instance. So for example, this is a instance of first image or first input. This is a instance of second image or second input. Features means if the image size is 28 by 28, then there will be 28 into 28 number of features. And label means its category, its class, right? Yes. So each image is an instance, right? Instance means a data point, input. Input is an instance. So here, since we are dealing with the images, so input means images, right? Similarly, label means its class, right? So first input class is, let's say, 5, or first input category is 5, which means label is 5. So label means output label. Then feature means the number of pixel values. So for example, if there are if we are having 28 by 28 images, then there will be total 784 pixels, right? So as you can see here, we are having total 784 pixels. So therefore, there are total 784 features, right? Where each feature is a pixel value, and pixel value can lie from 0 to 255 if we are having 8-bit images, right? Yes. So now we will have input data in a tabular form that include both features and label. Now using that matrix X and Y, where X is nothing but the input and Y is nothing but the output label, and we will use X and Y both to train a machine learning model, right? Okay. You can also plot any image. So because we have now converted images into a row vector, right? So originally we are having a 28 by 28 image, but after arranging this 28 by 28 images row wise, we are finally getting a row vector of size 1 cross 784, right? So if let's say if you want to display, if you want to uh, let's say if you want to print, or let's say if you want to display that row vector, then directly you cannot print, right? Directly you cannot display. So for that, what we should first do, we will first reshape 780 for 1 cross 784 vector to 28 by 28 image. Then only we can visualize this, right? Because we have converted this 28 by 28 image into a row vector, right? So row vector directly we cannot visualize. So if you want to visualize this image, then we have to first convert row vector to its original size, original size of 28 by 28. So if you want to convert a row vector to its original size, then how can we convert? For that, you will use reshape function, right? So again, we will use Matplotlib library, because if you want to plot something, then you will use Matplotlib. Matplotlib is used to plot plotting purpose, right? And you will import matplotlib.pyplot as PLT. So here, this PLT we are using as a short form for matplotlib.pyplot, right? And here we are using MPL as a short form for matplotlib, right? Okay. And here we are using X0. X0 means the first row, right? Because here the capital X is a matrix, right? Capital X is a matrix. So X0 means first row. X1 means the first row, right? Okay. So in programming language, index start from 0, right? So here the index 0 means first row, index 1 means the second row, index 3 means the third row, right? So whenever we write x in bracket 0, which means the first row, x bracket 1 means the second row, right? X bracket 2 means the third row, right? Yes. So here, since I'm writing 0, which means first row we are I'm taking, which means the first input data points I'm taking, right? Okay. Now this first input data point I'm reshaping to its original size, right? Because I have flattened 28 by 28 image to a row vector, right? So if I want to display that image, then I need to first reshape row vector to its original size. So for that, I am using dot reshape method to reshape a row vector to a 28 by 28 size, right? And after reshaping, I can, if I want to display that image, then I will use dot imshow method, right? So plt dot imshow method will display that image. And since here I want to show that image in binary, So that's why here I am using mpl.cm.binary, right? And since I don't want to show x-axis, y-axis, so therefore here I am writing plt.access is equal to off, right? And this plt.show will display that image, right? So if you display the first image, you will see image that looks like this, something like this, right? Okay, so this is the code. So here so for example, let's say if you want to visualize 36,000 image, then here you will write 36,000, right? So it will display 36,000 image, right? But before that, you need to first reshape this row vector into its original size of 28 by 28, right? Yes. Yes, so we will first divide dataset into two parts, training part and test part. We will use training part to train our dataset. We will use test part to evaluate our model performance. And then we will use performance metrics, some performance metrics to evaluate the performance of our machine learning model. That performance metrics can be accuracy or can be any other metric depending upon our dataset, our task, what type of task we are performing, right? So for example, let's say if we are doing classification, then we generally use accuracy. If you are doing a segmentation task, then there you may take intersection over IOU or some other metrics you can choose, right? So depending upon our task, our data set, we will choose some performance metrics to check how good our model is doing, right? Okay, so now let's discuss this first part. Divide dataset into training and test sample. So here we are first dividing because we are having total 70,000 images. So 60,000 images we are taking as a training dataset, and remaining 10,000 images we are taking as a test dataset, right? So for that, what I am doing here, I am taking first 60,000 images as a training data set and remaining 10,000 images as a test data set, right? Okay, so since I have already created x and y vector, right? Because here x means uh, the inputs and y means the output labels, right? So if there are 70,000 data points, then there will be 70,000 rows in X, right? And if there are, let's say, 784 features in each points, then there will be 784 columns in X, right? So how many rows will be there in X? 70,000. 70,000 is the total number of data points. And the number of columns will be 784 because there are total 784 features in each image. This y again will be a column vector of size 70,000 cross 1 because for each input we will have a corresponding output, right? Yes. So since we already have x and y, so x means input, y means x means input, y means output, right? Y means output label or target, right? Okay. So first 60,000 images I am taking as a training data set, remaining 10,000 images I am taking as a test data set. So here I am taking first 60,000 images as a training part, right? And then remaining 10,000 images as a test data set, right? Similarly, the output label for the training data are nothing but the y train, and the output label for the test data is y underscore test. So this y underscore test I will use to check the performance of our machine learning model, right? X underscore train and y underscore train. So x underscore train is nothing but the training input. Y underscore train is nothing but the corresponding output, right? So we are having training data, we are having output corresponding to training data. We will use X train, Y train to train our model, and we will use X test, Y test to check performance of our machine learning model, right? So any
So
doubt in this slide?
X test data should be 10,000 rather than 60,000, right? Or it's
Yes, yes. So X train and Y train will be 60,000. Data will be 60,000, right? So that's why here I am writing colon 60,000 colon 60, which means 0 to 60,000 minus 1, 0 to 60,000 minus 1. And here I am writing 60,000 to the number of columns that we have, number of data points that we have. So it will automatically take remaining 10,000 columns, remaining 10,000 data, right? Any doubt here? So
but why we cannot put 10,000? Whatever left out, why we are putting X test and
so
Y test
yes,
also
you can also do. So actually here what you can write here 0 to 59999, right? And this place you can write 60,000 to 70,000. You will get the same values, right? Okay. So after dividing data into two parts, training and testing. So here we will use X underscore train and Y underscore train to train our model. And this X underscore test and Y underscore test, we will only use to evaluate performance of our machine learning model, right? So training part we will use for training, testing part we will use to evaluate our model, right? Okay. Then we will train our model using training data. So since we are doing supervised learning, so we will use data and its label to train a machine learning model, right? Okay. So for simplicity, let's first,
So,
yes.
sorry, sir. So while explaining, are we going to be also do the on the lab also how it's performing this every steps?
Yes, sir. So I've already shared this Jupyter notebook file, and here in slide also I'm covering the code part, right? So this train test split, so I've already covered, right? So by just writing this line of code, you can get training data and test data, right? So as you can see here, the first 60,000 points we are taking as a training data, and the remaining 10,000 points we are taking as a test data, right?
So are this dividing? It is the random one, or
No, no,
we
no.
are
We are just taking first 60,000 point as a training data and remaining 10,000 point is the test data. But yes, you can also use stratified technique, right? So you can also use techniques to better divide these data points, right?
correct? Because there are chances it could be biased information, na?
Yes, yes,
Like
yes, yes.
first or last one.
It may possible if data are not here the assumption is uh, but it may create a problem when let's say all digit zero images are let's say sequentially arranged, all digit one images are then sequentially arranged next after the digit zero, right? And then digit two, all digit two images are arranged after digit one images, right? So then it may create the problem, but in this data set these images are already arranged randomly, right? So it's not a problem, but yes, it's not a good idea to divide in using this scheme, right? So then either we should divide using random policy, right? So randomly we can divide training and testing part, or we can also use stratified techniques, right?
So where did you share this notebook?
Notebook I have shared in the chat section.
Um, you know, see, actually.
So IPython notebook is there. Classification dot IPN IPYNB.
In this meeting chat, you think?
Yes, yes, yes.
I can't see it, Praveen.
I also
Okay,
can't
okay.
see
So
that.
let me share it again. Now, can you see notebook file?
Yes.
Yes, sir.
Okay, okay. Yes, so I already I also shared the slide that I'm using in today's session, right?
No, so slide is not available.
Slide
Only
is still
Python.
uploading.
Okay.
Mhm. Okay, so let me check one more time. Yes, so it is still uploading. Yes, uploaded. Okay, so here our goal is to build a machine learning model to solve a multi-class classification task. But for the sake of simplicity, we will first train a binary classifier, right? So in binary classifier, we will solve a binary task, right? So where we will predict one class, and there are total two classes, right? Okay. So for the sake of simplicity, let's assume our task is to predict whether a given image is a handwritten 5-digit image or not, right? So again, for any given image, we have to predict whether this image is a 5-digit image or not, right? So since here we are solving a binary task, so therefore this is a binary classification task, right? And this type of detector we are calling is 5 detector, because this detector or this model is detecting 5 digit, right? Okay. So for that, what we should first do, we should first change the output labels, right? Because inputs we already have. There are total 70,000 data points, 70,000 images we already have. Some images are 5-digit images, some images are not 5-digit images, right? So maybe image maybe image can be digit 0 image, 1 image, 2 image, like that, right? Okay. So here we need to first change the output labels, output vectors, right? So for that, what we can do, we can simply use this Python line. So here, Y train we already have, right? Y train means the output labels for training data points. So if, let's say, if we are dividing data points into, let's say, 60,000 and 10,000, then in training training output labels, there will be total 60,000 labels, right? Okay. So the size of this y underscore train vector will be 60,000, and the size of this y underscore test vector will be 10,000, right? So this y underscore train is nothing but a 60,000 dimensional vector, right? 60,000 cross 1, and the size of y underscore test will be 10,000 cross 1. So it's a column vector of size 10,000. Y underscore train is a column vector of size 60,000, right? And since here we are implementing a detector that can detect 5 images, so therefore either image can be 5, or it is not a 5-digit image, right? So it's a binary task, right? Okay. So if the image is 5, so here we are using y underscore train equal 5. So if this condition is true, which means it will store there 1. If condition is false, then it will store false, right? So if image is a 5-digit image, then this condition is true, it will store 1. If this condition is false, then it will store 0. So 1 means true or 0 means false. So or you can think 0 or 1 in binary, right? Not in decimal. So or you can think it will store true or false, right? So if this condition is true, which means it will store true. If this condition is false, it will store false, right? Okay. So
But
here,
then,
yes,
sorry,
yes.
Dr. Praveen, so this is when we say y underscore train equal to 5. So
Mhm.
should we not provide the index also, because y underscore train has
No. So
60,000?
Python will do automatically. So here y underscore train is a vector and this 5 is a scalar. So we are doing comparison between a vector and a column vector and a scalar. So Python, what Python will do? Python will compare this value element wise, right?
Okay, for all the 60,000 ones.
Yes. So for example, let's say if you have a vector of, let's say, values, let's say 5, 6, 5, 1, and 2. And if you are writing equal 5 in Python only, right? In Python programming language, what it will do? It will do this comparison with each element of this vector, right? So in output, what it will give you 5 equal 5 condition true, 6 equal 5 condition false. So second element will be false, then true, then false, then false. So you will get vector of true and false of size of same size. So here the size is column vector of size 5 by 1, right? So again you will get a vector of size 5 by 1, right?
Okay,
Okay.
thank you.
So after writing y train underscore 5 and y test underscore 5, you will get a vector of true and false, where true means the image is a handwritten digit 5 image, and false means image is not a 5 image, digit 5 image, right? Okay. So now we already we have the corresponding output, corresponding ground truth, right? Because we have changed our problem, right? So now we are not predicting handwritten digits from 0 to 9. We are predicting whether this image is a 5-digit image or not, right? So we want, so let's say if this image is a 5-digit image, what we want in output? True. If not, then what we want in output? False. So this is why we are converting output labels in this true false format, right? Okay. Now we will use stochastic gradient descent classifier to train a machine learning model. So SGD I will discuss later, but here you can understand SGD is a method using which we can train a machine learning model, right?
Dr.
Because
Praveen,
now, yes,
one, like I was just running the IPython notebook that you have provided actually. In that I'm getting a key error when I'm if you can go about X of 36,000
Mhm. No. So
something.
you so where are you running executing this IPython notebook? So are you running
On
in
Jupyter.
so in
On Jupyter
local
or
machine, or you are
in
running
my
in
local lab.
CloudxLab?
Not in CloudxLab, in my local Jupyter notebook.
Okay. So in local, maybe because this is the old Jupyter notebook file, so some packages are not compatible, right? So so if you execute this Jupyter notebook file in CloudxLab platform, then you will not face any problem, right? Because of package conflict, maybe you are getting some problem, right? Because in Python there are lots of version, in packages also
No, all
syntax
the
are getting
versions that
changed.
you have given assert
Mhm,
statements that is passing.
No. So for example, here let's say maybe you are using some other version of Python. So because Python 3.6 is a very old version, right? So and here and yes, in each version we are having different syntax, right? So maybe due to syntax problem, or you may
Uh,
face any problem, right? So it's better to upload that IPython Jupyter notebook on CloudxLab, right?
Okay.
So what you can do, you can go in this MyLab section, and then you can open IPython Jupyter notebook file, and from here you can upload that file, right? So if you click this upload, it will upload the notebook file that I've shared in the chat section, right? And then you can execute. You will not get any error, right?
Yeah,
Okay.
sir.
Yes. So here I'm using SGD classifier to classify whether a given digit is a 5-digit image or not. So SGD I will discuss later, but here you can think SGD is a method using which we can train a machine learning model, right? So SGD is a classifier, and for the sake of simplicity, assume we are only having two features in our input data points. So this x-axis we are having first feature, y-axis we are having second feature. So each training point, each training input is having uh, two feature values, x feature and y feature. So this x-axis we are having first feature, y-axis we are having second feature. So since we are having two features in each data point, so therefore in 2D we can represent each data point as a point, right? Because each data point is having two values, right? Feature 1 values and feature 2 values. Okay. So all these points belongs to, let's say, class 0, and let's say all these points belongs to another class 1. So we are having two class data, class 0 data and class 1 data. And our goal is to separate out these two class data, right? So as you can see here, by learning this linear classifier, we can separate out these data points into different classes. So for example, let's say if data points lies above this boundary, above this classifier, then its class is 0. If data points lies below this boundary, or this below this classifier, which means class 1, right? So here I am taking a very simple example to show you how can we use classifier to classify data into multiple classes. But the same concept we can generalize where when we have more than two features. And in fact, in our case, we are having more than two features, right? Okay. So here, if for this simple problem, if you are estimating this classifier, then here this classifier is nothing but a equation of line, right? So in if you want to estimate this equation of this line, then we need to estimate two parameters: slope of this line and the intercept of this line, right? Because if you change the slope of this line, orientation will change, right? If you change slope, orientation of this line will get changed, right? If you change c value, if you change this intercept value, the shifting of this line will get changed, right? Okay, so we need to learn here the slope, optimal slope and optimal intercept value, right? So suppose, let's say, if you are learning y is equal to mx plus c, so here we need to learn these two parameters m and c. M means slope of a line and c means intercept, right? So suppose this is the equation of line. So here this theta will tell you tan theta means slope, and this value is intercept c, right? Okay. So since here we are using two features, so let's say two features are x1 features and x2 features, right? So if we are learning a line equation of this line, then the equation of line will be W1 x1 plus W2 x2 plus some bias is equal to 0, right? And you can convert this line into this form, right? Okay. So the point that you can note here, since we are here using two features x1 and x2, and we are learning a linear model, so therefore it will be a linear combination W1 x1 plus W2 x2 plus b, right? So in machine learning terms, this W1 and W2 are nothing but the weight of this model, right? Weight of this this classifier, weight of this model, and this B term is known as bias term, right? So here, if I'm saying we are learning this model, which means we are learning optimal value of W1, W2, and bias term, right? So if I somehow calculate optimal value of W1, W2, and B, I can get the equation of this line, and using this boundary, using this line, I can easily classify. I can easily separate out class 0 examples from class 1 example, right? Because if I know this equation of this line, then I can use the simple rule. If data point lies above this boundary, above this class, above this line, then class label is 0. If data point lies below this line, then its class is 1, right? Okay. So this HGT classifier I will discuss
Okay,
later,
Praveen.
but yes.
Why it was like W1 x1 W2 x2? Like the bias term is the intercept, right? That's what I understand. Um, so this is like a 3 feet. I mean,
No, because here we are having two features, x1 and x2, right? So let's say you can convert in this form, right? So for example, let's say what you can write here, let's say W2 x2 is equal to, let's say, minus b minus W1 x1. Then you can divide this W2 term. What you will get, x2 is equal to minus b by W2 minus W1 by W2 x1. So you can think this term minus W1 by W2 as a m and minus b by W2 as a c. So it will get converted to this equation, y is equal to mx plus c, right? If you think this is a y axis and this is the x axis, right?
okay.
So here I'm using the standard form, right? If I'm having n number of features, then I will learn model something like this: W1 x1, W2 x2, and so on, Wn xn plus bias is equal to 0, right? So since here I'm only using two features, x1 and x2, so therefore I'm using W1 x1 plus W2 x2 plus b is equal to 0, right? So this is a linear model, right? I'm not saying non-linear. In non-linear model, we will have a combination of x1 and x2 also, right? But in linear model, since degree cannot be more than 1, so that's why we will have x1 alone, x2 alone, x3 alone, and so on, right?
So since we have 700 something features, we will have that many terms plus the
Bias
bias
term.
term.
So which means if we are having 768 features, then we have to learn a weight vector of size 768 plus one bias term, right? So you can say number of features plus one. So here let's say we are using two features, so the unknown parameters are 2 plus 1 3, right? If n features are there, then number of unknowns are n plus 1, right? But this is only true for the linear models, right? For non-linear model, it is not true, right? Okay, so I will discuss this later. So here you can think uh, using this HGT classifier, we are learning a machine learning model and using that machine learning model, we can do the classification task. So as you can see in this example, right? If point lies above this line, above this boundary, then class 0. If point lies below this line or below this boundary, then class 1, right? So there we will have some different rules, right? So using that rule, we can classify points into its classes, right? Okay, so this slide I have already covered, right? So here we have to calculate optimal value of W parameters and optimal value of bias parameter, right? So here the capital W is nothing but the W1, W2, right? Because we are having two Ws here, W1, W2, and this bias term, right? Yes. So this HGD you can classify, we can use even for the large data set, even we have the huge number of data points, we can also use. So for example, in this case also, we are having 70,000 data points and we are using HGD classifier. And this classifier is well suited for online learning because in this classifier, we will take input one by one, right? So we will train our model using one input at a time. So since we are using one input at a time, so even if the data we are getting in an online fashion, we can use this classifier model, right? Because in some cases, it is the restriction that we can only train that model when we have the complete data, right? So it is not the case with the SGD classifier, because since in this classifier we will train our model one point at a time. So since we are only need one point at a time to train this model, so therefore, even if we are getting data sequentially, we can use HGD classifier, right? Okay, so now let's yes, so let's discuss this our original problem. 5 versus not 5 classifier, right? So for that, I'm using here HGD classifier. So I will first import HGD classifier. For that, I will use scikit-learn.linear model, and from scikit-learn.linear model, I will import HGD classifier. And here I'm using random state is equal to 42. So this random state I'm using to ensure reproducibility, right? Because when I next time, let's say I'm again writing HGD classifier, and let's say I'm not using this random state, or let's say I'm using some other number other than 42, or let's say 44 or something like that, then my result may not match, right? Because the stochastic gradient descent classifier depends on uh, stochastic process. Stochastic means randomness. So some randomness are there. So if in this learning process, if we have some randomness, then every time if you train your model from scratch, you will get a different result, right? So to ensure reproducibility, here we are using random state, right? So if, and yes, here you can write any number. Random state is equal to 42, 40, whatever number you want, you can write it, right? And this random state is not mandatory. You can also skip that, but then the reproducibility is not guaranteed, right? So every time you will get different answer, because this classifier involves some random process, right? Using which this model learns the optimal parameters, right? Okay. So here first we are creating an instance of HGD classifier, and then we are fitting our data to this HGD classifier, right? And here I am passing X train and Y train, where X train is nothing but the training data points, and Y train underscore 5 is nothing but the corresponding output labels, right? Because I have already converted outputs to a vector of true and false, right? Because now I want to predict whether the given image is a handwritten digit 5 image or not, right? So I need this type of output label. So I have already convert y underscore test 5 using this condition, right? A vector of true and false. Yes. So here I'm learning a HGD classifier, right? Now after learning a classifier, I will test its performance using test data, right? So to predict its performance, I will use here dot predict method, right? So HGD underscore CLF is nothing but the my HGD classifier, right? So first I will fit uh, uh, this HGD classifier uh, to our training data, and then I will use this HGD classifier model to test to make prediction, right? Okay, so here I am taking first input x0, and if I pass first input as a input to this model, it is predicting its type, which means model is predicting true. True means first input is a handwritten digit 5 image, right? So I will use dot predict method uh, to predict, right? So for any given image, I can use this trained model to make a prediction at test time, right? Okay. So now let's discuss some performance metrics, because how can we uh, how can we uh, know that whether our model is doing good or not, because we need to evaluate its performance, right? Now this performance matrix we will choose depending upon our task, our data set, right? Okay, so after training our model, for evaluating we will use performance matrices, right? Now, there are several types of performance matrices. We can use accuracy, we can use precision, we can use recall, F1 score, ROC, we can use, right? Okay. So let's discuss these performance metrics one by one. So let me first discuss the cross validation or accuracy. So this cross validation I've already discussed, right? So there are two types of performance that you can measure. Either you can directly test model performance using test data, or you can use cross validation to test model performance, right? So case one is nothing but the where you are testing model performance directly on the test data, right? Yes. Yes. So we have trained our model. We have trained our model using dot fit method, and here we are passing input data points and corresponding labels. Right. Now for the testing part, uh, there if you are using test data, then you will evaluate, you will use dot predict method for the test data, or you can use the cross validation to evaluate its performance, right? So cross validation I've already covered, right? So in cross validation, what we do, so for example, let's say if you are doing 5-fold cross validation, then the training part you will divide in 5 parts, right? Training data you will divide in 5 parts. The remaining 4 part you will use to train your model, right? And the left out part you will use as a testing part, right? So for example, let's say if you want to do 3-fold cross validation, then you will divide training data in 3 parts, right? Any two part you will use for the training, and the remaining part you will use for the testing. So since here we are doing 5-fold cross validation, so therefore we will divide training data into 5 parts. And so for example, here second, third, fourth, and fifth we are using for training our model, and first part we are using for testing purpose, right? So you can think like the second part, third part. So for example, let's say if uh, there are let's say 100 data points. So if there are 100 data points, in each part there will be 20 data points, right? So first part there will be 20 data points, second part 20, third 20, 20, right? So therefore total number of data points are 100, right? So if there are 100 data points, you will divide 100 data points into 5 parts, right? Now the first part you will evaluate your model, and the remaining part you will use to train your model, right? Okay, so you will train your model using these 4 parts, and you will evaluate your model using test part, right? And after evaluating, you will get some performance metrics, right? So for example, here you are getting performance P1, right? Now this performance can be anything. Performance can be accuracy, can be precision, can be recall, right? Similarly, you will use this part, this part, this part, and this part to train our model, and you will use this part to test our model. And when you are testing your model using this part, you are getting P2 performance number, right? Similarly, you will use these parts to train your model and this part to test your model. And now in this case, you are getting P3 performance. So likewise, you will get P4 and P5, right?
Dr.
Now,
Praveen, sorry,
yes, yes.
why have we divided? I mean, I understood the 5 folds,
Mhm.
but what are these 5 rows?
No. In 5-fold cross validation, we will divide the complete data into 5 parts, right? So this is the part 1, part 2, part 3, part 4, and part 5. Now we will use, so let's say if let's say if you are doing k-fold cross validation, cross validation, in k-fold cross validation, you will divide training data points into k parts, first part, second part, and so on, kth part, right? Now in each iteration, you will use k minus parts as a training, and one part as a testing.
Okay, and then how many iterations will be there?
There will be k
That-
iteration,
Okay, got it.
right?
Sorry, got it. Thank you.
Yes, so for example, let's say here the first part can be the test part, second part can be the test part, third part can be the test part, fourth part can be the test part, fifth part can be the test. So if you are doing k-fold course validation, then there will be total k such combinations, right? There will be k rows, right? Or there will be k, not rows, there will be k iterations. So this is the first iteration, second iteration, third iteration, and fifth iteration, right? So in first iteration, you are getting P1 performance, second iteration, P2 performance, P3, P4, and P5. So now what you will do, you will calculate the average performance. So P1 plus P2 plus P3, P5 divided by 5, right? And this is nothing but the your model's average performance, right? So in case 2, you will calculate this average performance, right? Now this performance can be the accuracy. So if this performance is the accuracy, then you will calculate average accuracy. If you are doing a 3-fold cross validation, then you will calculate average of 3 accuracies, right? Okay. So in first method, we can use either test data to evaluate our model performance, or we can use cross validation to evaluate model performance, right? And for if you are doing cross validation, then you can use cross val score function in scikit-learn that can be used to perform cross validation, right? So you can use cross val score function to use cross validation. So for that, what you can do, you can import from scikit-learn.model selection, you can import cross val score, and then you can use cross val score function, and here you will pass your classifier. So here our classifier is this HGD underscore CLA, right? Because our model is HGD underscore CLA, which is nothing but the HGD classifier, right? So we will pass our classifier here. Yes, here. And then we will pass training data. We will pass corresponding labels, corresponding training labels. Here we will write, mention cross validation. So for example, if you want to do threefold cross validation, you will write here 3. If you want to do five-fold cross validation, you will write here 5, right? And then you will write here the scoring. Scoring means on what basis you want to evaluate the performance of your model, right? So for example, on the basis of accuracy you want to evaluate, here you will write accuracy, right? So a scoring parameter, so it will evaluate your model using accuracy measure, right? Any doubt here? Okay. So if since here we are doing a threefold cross validation, so therefore you will get 3 performance measures. So just like here we are doing 5-fold cross validation, so we are getting 5 performance measures, right? And here for the scoring we are using accuracy, so therefore you will get 3 accuracies, right? So here this is the accuracy for the first iteration, accuracy for the second iteration, accuracy for the third iteration. So as you can see here, the resulting accuracy is above 95% for each iteration or for each fold, right? So do you think this 95% is a very high accuracy in this case?
I would think so.
Or is there any problem in with this classifier? So here what we are predicting whether a given image is a digit 5 image or not, right? Now in our data set we are having total roughly 70,000 images, right? So if we are having 70,000 and assume all images are so for example, let's say we are having total 10 classes, so roughly 7,000 images we can assume for each digit, right? So for 0 digit we are having 7,000 images, for 1 digit we are having 7,000 images like that, right? Which means 9 into 7, right? So 5 digit images we are having 7,000, right? 7,000 images are there for digit 5, and remaining images are for the known 5-digit images, right? So do you think we have skewness in our data set? Our data set is biased, right?
Mm.
So this accuracy may not be a good criteria here, right? Okay, so let me take one example here. So here, if
Why accuracy is not good if the class is biased?
yes, because we are having a skewed classes. Class distribution is skewed, right? So assume we are having assume for the sake of simplicity, assume we are having 100 images, and on an average for each digit we are having 10 images. So for example, for digit 0 we are having 10 images, digit 1 we are having 10 images, and so on. For digit 9 we are having 10 images, right? And here what we are predicting, we are predicting 5 versus not 5, right? So in this 5 case, now how many images are there? Only 10. And for the not 5, how many images are there? 90. Which means not 5 cases in this class, not 5 class, there are 90 images. And in 5 class, only 10 images are there, right? So since here we are having a a biasness in our class distribution. One class is in extreme majority, other class is we are having in minority. So in that case, accuracy may not be a good criteria. So I'm not saying accuracy. Sometimes accuracy you can take, sometimes you cannot take. But yes, you cannot totally rely on the accuracy, right? So let me give you one example here. Yes. So if you learn this HGT classifier, and if you use cross validation as a accuracy measure, right? If you use cross validation as a accuracy measure, then we are getting above 95% accuracy, right? Which means our model can predict whether a given image is a digit 5 image or not with 95 more than 95% accuracy, right? Our model can predict whether a given image is a digit 5 image or not with a accuracy above 95%, right? Okay. Now let's build another classifier which classify every image as not 5, right? And we are calling this classifier as a never 5 classifier. Never 5 classifier means this classifier will classify every image as not 5. Even if the image is a 5 image, it will classify not 5 image, right? Okay. So clearly for this model, we are not learning anything, right? So here we are not learning anything, and we are doing some we have done some rule based programming, right? Because for every image we are just predicting not 5, not 5, right? Okay. So this is the code. So here, as you can see, in fit functions, we are not doing anything. We are not doing anything. And for the predict functions, we are simply returning zeros, because 0 means not 5, right? Because here we are solving a binary classification task, right? 5 versus not 5. So here 5 means yes. Here 5 means true or 1. Not 5 means false, yes, or 0, right? Yes. So in this code, what we are returning, we are just returning a vector of 0, which means, and yes, this 0 doesn't means 0 in decimal. 0 means in Boolean, 0, 1 in Boolean, right? In binary, I am saying. Okay. So since here I am returning a vector of zeros, which means vector of all false entries, all false values, which means what I am predicting, not 5, not 5 for all images, right? Yes. So this code will return simply a vector of all false values, right?
Dr.
So
Praveen,
yes, yes.
I'm sorry, but I didn't understand. So for
Mhm,
every image, it will return as not 5, is it?
mhm, mhm.
Means whatever you pass, what are we doing here?
No, no. So we are not learning anything. I'm just trying to show you that even this simple classifier where we are not learning anything can give you the very high accuracy in this case,
Oh.
right? Because clearly here we are not using any machine learning technique, right? And in fact here we are not learning anything. We are just following a simple rule that for every image it will predict not 5, right? Yes. So if you implement this classifier, and if you evaluate this not 5 classifier that predicts not 5 for every image, and if you again use same metric accuracy, again use the same cross validation 3, because in previous case also we are using threefold cross validation, accuracy as a metric, right? So now for this classifier also, if you use uh, threefold cross validation accuracy as a metric, you will get 90% accuracy, and 90% again a big number, right? Which means even this dumb classifier can achieve 90% accuracy, which means if we are having biasness in our classes, one class we are having in extreme majority, other class we are having in minority, then accuracy is not a good measure of performance, right? Any doubt here? Because this dump classifier, using this dump classifier, you are able to achieve 90% accuracy, right? So here, why are we getting 90% accuracy? Can you tell me?
Because only 10% are images of 5.
Yes, exactly. Because 10% of images we are having digit 5 images, and remaining 90% images we are having not 5 images, right? And we are predicting not 5 for every image, which means 10% or 10% of time this classifier will be wrong, and 90% of time this classifier will be correct, because 90% of images belongs to not 5, and only 10% of images belongs to digit 5, because there are total 10 classes are there, right? And we are assuming that each class is having equal probabilities, right? Which means the number of samples, number of data points for each classes are equal, right? Okay. So since in our data set 10% of images we have for digit 5, and remaining 90% images we are having for other digits, so therefore even this dump classifier can achieve 90% accuracy, right? So if we have skewed data set, if we have data set where some classes we are having in majority, other classes we are having in minority, then we cannot rely only on accuracy, right? So I'm not saying we will not use accuracy. You can use accuracy, but with accuracy we should also use some other performance metrics, right? Okay. Yes, so this slide I have already covered. So even with this dump classifier, we can achieve 90% accuracy, right? Okay, so accuracy may not be a good performance measure when dealing with skewed data sets, right? Okay, so let's say your friend has built a model which classify an image into a male or female. So again, we are doing a binary classification task, right? We are solving a binary classification task because model is predicting whether a given image is a male image or female image, right? Okay. So if you are building a model which classify image into a male or female with 99% accuracy, then you should ask your friend for the is there any biasness present in the data set, right? If let's say 50% are male images, 50% are female images, then this 99% accuracy is a good metric, good evolution metrics, and you can use this, you can trust that model, right? If you have the balanced data sets where roughly 50% images you are having for male or female, right? But let's say if you are having 80% male images or 90% male images, then you cannot trust this accuracy number, right? Because now you have the biased data set unit, right? Yes. So here, if we are building a machine learning model to predict male or female images, then we should first check in our data set what percentage of images belongs to male category and what percentage of images belongs to the female category, right? And if we have any bias in our data set, then we cannot trust on accuracy. Yes, so for example, 80-20, then accuracy is not a good performance metric, right? Yes, so even if you are getting 99% accuracy, you cannot trust this model, right? Because we are having a skewed data set, right? So we need a better measure of performance to evaluate the performance of our model, right? So what we can do in this case, we can use precision, we can use recall, we can use F1 score, we can use confusion matrix to evaluate the performance of our model, right? Okay. Yes. So I think I should stop here, and I will discuss this confusion matrix and other performance metrics in the next session, right?
Okay.
And yes, please download the IPython Jupyter notebook file and the today lecture slides from chat section.
So Dr. Praveen, today's lecture slides will be covered in tomorrow's quiz, or
I think only the end-to-end part will be there.
okay. So whatever was done until last week.
Yes.
And will there be any, will there be any questions related to coding, like the scikit-learn or other examples, or it will be mostly theory
So
based
it will
questions?
be mostly objective type questions, but yes, I already covered the coding part in slides. So if you if you can understand the code that I've discussed in the slide, then the questions are easy, right?
Okay.
So Dr. Praveen, one last thing. So whatever the slides that you have shared until last week, the slide deck, so that will be part of tomorrow's quiz, correct?
Yes, end-to-end machine learning project.
Okay.
And sir, we'll have the last, the quiz will be in the last 15 minutes, no?
Yes, yes.
Okay, sir.
No, there are like some 4 or 5 slide decks that have been shared, end to end, then data pre-processing, data and features. So only the end to end part will be there.
Yes, only because the other slides I have shared just so that you can get the better idea, right? So because I created some visualization, so that's why I shared with you, right? So but yes, the syllabus is same, right? So because in those slides also I have covered the same topic.
Okay, okay.
Okay, so thank you very much for
So
joining.
Praveen,
Yes, yes,
before you
yeah, yes.
just want to check the number of files you have shared. Like I got like 4 or 5 different kind of, presentation or PDF from you, but not sure if
Yes.
that is all or I missed out on any.
Okay, okay. So today I shared this
Yep,
classification PPT and classification IPython
yep.
notebook file. And for end to end, I shared. Okay, so what I can do, I can again share all these files in chat section, right? So in case if you do not have any file, you can please download these
Yep.
files from
These
me.
are the files, right, that you have shared before. But
Yes, yes,
yeah,
yes.
okay.
Okay, so let me share all these file again.
Are you sharing in the Zoom chat or
Yes, yes,
are
I'm
you
sharing Zoom
okay?
chat. Please download. So some files
Okay.
are still uploading.
Yeah. I mean, if you disconnect the call now, we
No,
won't
no,
be
no, no,
able
no.
to.
So I will wait 2-3 minutes.
Okay.
So it's so pin drop silence. I can hear the clock seconds.
Yes, yes.
Nice.
Okay, so please download these files. Then I will close this meeting, right? After 3 minutes.
So totally 5 slides or 5 things you have shared. No, no.
Yes, yes, yes.
Okay, sir.
Sir, can you also send that PDF file of data progressing regression? Is that necessary for that tomorrow's quiz?
Which file?
That data pre-processing and regression PDF file.
Yes, no, no, it is just the same file, end-to-end machine learning
Okay,
MD.
okay. Yes, sir.
So here only this file, end-to-end machine learning PPT is important. Other files, uh, I just have some visualization that you can understand the problem better, right? But that is not a part of use. But even if you go through these slides, you will get a better idea, right?
Okay. And for this end-to-end machine learning, that was like all your lectures until last week were
Yes, yes,
part of this end-to-end machine learning, right?
yes, yes, yes.
And those all recordings are also available, I assume, on the
Yes, I think
cloud.
yes, all recordings are available.
Okay. Okay. Wait.
Okay, so can I close this meeting now?
I'm unable to download that four dot classification file.
Okay, okay, let me see. Okay, maybe the size of this slide is big, right? 20, approx 22 MB.
Yep, all done.
Okay, okay.
Okay, thanks, Prabhu.
Thank you, Rajesh.
Thank you. Bye-bye.
Bye.
Thank you.